Assalamualaikum and have a good day to all the panel. Dr. Afifah Binti Yahaya and Associate Professor Wan Ahmad Najmi bin Wan Mohamed and the viewers of my presentation video. I hope everyone doing well and safe during this pandemic. Thank you for watching this video. I am Mohamed bin Azahar, finance ministry student of Bachelor of Engineering Hans Mechanical, and I am under supervision of Professor IRTS Dr. Yupiter Harangan Prasada Manurung and Miss Siti Nursyahirah Ahmad as co-supervisor. In this video, I will present and talk about my final year project, effect of heat source model on substrate deformation and thermal distribution of wire up additive manufacturing using numerical simulation. As you can see here, in this video presentation, I will discuss about the introduction, problem statement, question, the objective, methodology of the project, result, significance of work, and conclusion of the project. Before we jump to the first topic of the presentation, let me tell you about additive manufacturing. Over the years, for the manufacturing industry, additive manufacturing become one of the huge and extensive innovations in the production of metal parts. Additive manufacturing is a technology have capability and potential to lessen the cost by reducing the material wastage and time to market. Additive manufacturing also can enable the creativity of design freedom and reduce the limit of manufacturing of complex assemblies formerly made out of numerous subcomponents. The system of additive manufacturing will be made up by the combination of feedstock, heat source, and motion system. Additive manufacturing uses data computer-aided design, CAD software, or 3D scanners to direct hardware to deposit material, layer upon layer, in precise geometric shapes. Now let's start with introduction. Wire-up additive manufacturing, also be called as WAM, is one of the most effective additive manufacturing branches. Wire-based additive manufacturing is basically taking an advance from gas metal operating power source, an industrial robot, and software that combines the robot's motion with the multi-axis positioner to lay down successive well bits to create a free-form 3D shapes. WAM also allows the production of large-scale structure elements that are free of geometrical restriction in terms of size or form. After years of research and development, WAM has established itself as a technology for the production of metallic parts, with improved mechanical characteristics that are both scientifically sound and commercially feasible. However, from a commercial standpoint, there are a number of difficulties to overcome, such as expensive equipment and material price. In context of the complexity involved in one process, optimization tools, sustainable manufacturing, and simulation models are required in order to save time and money via the elimination of expensive trial and error. For this research, it will be done by using a numerical simulation. Next, the most important significant boundary state in numerical analysis is the heat source model. Therefore, the appropriate resource model must be chosen accordingly to the welding process. Hence, the heat source model that will be applied in this simulation of FE model is double ellipsoid heat source model by Goldberg and rectangular heat source. Now we proceed to the problem statement. As mentioned before, complexity of the model requires many resources to achieve a better final product. So, simulation of the finite element method offer an efficient manner to research modification of this issue. Next, the effectiveness of the heat source model and FE modeling need to be considered due to its most important part in the numerical simulation. Before starting the project, there are a few questions needed to be answered. First one is, what parameter of wire are additive manufacturing model to be applied in the research? Next is, what is the software of FEM will be used to generate a simulation method model for comparing two different source models? Another question is, what the outcome of one process that will be compared by using two different heat source model? And the last one is, which heat source model offer the least computational time for simulation? So for answering the research question, here is the objective of the project. The first one is to determine the parameter of wire additive manufacturing model. Second objective of this research is to generate a numerical simulation by using MSCMA as FEM software for comparing two different source models. Third is to characterize the substrate deformation or dispersion and temperature distribution induced by one process using two different sources. Lastly, to identify and compact the computational time for FE modeling to complete the simulation. Okay, now we proceed with methodology, where the procedure and technique used to identify and achieve the objective of the project. As you can see on the screen right now, here is the flowchart of the whole project in FYP1. For this FYP2, we start by build the WAM model by using MSC Mark. So here is the flow and step for modeling the WAM model using MSC Mark, starting from geometric modeling till analyzing the result. I will discuss more detail on the next slide for the modeling WAM model for numerical simulation. On the screen right now, we can see there are three elements of WAM model that consist of plate, rectangular shape well bit, and table. Plate with dimension of 200 mm length, 97.5 width, and 8 mm thickness. For rectangular shape well bit, the dimension is 190 mm length, 7.5 mm width, and 2.5 mm for thickness for each string, where the model is set for 10 layers with 3 string model. A complete deformation of the finished component can be only achieved by fabricated part has been cooled down completely to ambient temperature, and all clamp and the support have been removed. As a solution, an extra element which is stable had been added to simulate the wiping away of the support and base plate from the end component of the model. Since the geometric form of the workpiece is relatively uncomplicated, quad mesh meshing was selected as the kind of meshing to be used. The use of a simpler mesh is done in order to reduce computation time and make the modeling process easier, since there will be less strain and change in form. For this 10 layers testing WAM model, the material applied in for wet filler is SS316 stainless steel and low carbon S235 for base plate and the table of the model. Most material properties were imported into FEM simulation using existing database from MSC Mark material properties. For the orientation of the weld path, all the weld filler elements had been assigned one by one from the element L1S1 to the end of the element L10S3. For the path input method, the middle node on the top of the string element had been selected as the path from front to back, while for the orientation input method, the middle node of the bottom of the element had been selected as the orientation of the weld path. All the direction was defined to be perpendicular to the surface of the weld filler. The direction of the weld path had to be in zigzag direction. As for the second string must start from the back of the part to the front of the part. This method applies for each layer. On the screen now shows the weld path that represented by the blue arrow in the FE software. In this WAM simulation, just an initial state of thermal condition had been defined. All the elements in this simulation which was in the weld filler, plate, and table were defined to be at 30 degrees Celsius. Next, thermal and structural boundary conditions were applied in combination with each other for the boundary condition. There were phase film boundary conditions shown in figure 7 was added to the surface of each weld filler element in order to simulate the cooling effect of the surrounding environment. All the phase film boundary conditions of weld filler were included with table and plate. It is necessary to consider the consequence of heat loss from radiation and convection so as to properly design the boundary condition. The temperature of the ambient was set at 30 degrees Celsius while it is not in use. To study the substrate deformation on WAM model on arm clamp side of the substrate, a clamping force of approximately 100 Newton were applied on the top left and bottom right side of the specimen, with the clamping force directed toward the y-axis. The direction or location of the force applied shown in figure 8. As mentioned before, the most important and significant boundary state in numerical analysis is the heat source model. Therefore, the appropriate heat source model must be chosen accordingly to the welding process. There are two heat source models were applied in this WAM model and compared. The heat source model was set when assigning the volume wet flux boundary condition in thermal structure analysis. Double ellipsoid biconduct and rectangular heat source model had been chosen as the heat source for this motion. Double ellipsoid heat source model are two elliptical regions in the heat stream, one in front of duct and one in the center, and were commonly used in GMAW welding process. The figure displays the double ellipsoid heat source model of conduct with the geometrical parameter A, B, and C that are independent values that can be changed into other values for the front and rear quadrants. For rectangular heat source model, the user defines wet flux subroutine which has been modified and applied
in the MSC mark code. The parameter applied in this one model is 3.4 kilowatt power with a travel speed of 5 mm per second. These parameters were taken from previous experimental data. Table 2 and 3 show the dimension of its source model applied in the FEM simulation. Before run and submit the simulation for result analysis, it is necessary to construct a load case in which all the loads and boundary conditions are applied, with a constant time step of 0.5 seconds each increment. The simulation time is set to 38 seconds for each string of welding pump and constant time step of 1 second, with load case time 120 seconds for every layer cooldown time. An additional load case was implemented to deactivate the substrate material, and the table once the cooling down time of 250 seconds was complete at the end of third string of 10 layer of the wet filler. To create a more accurate simulation, the total increment of 3680 may be raised. However, this would significantly increase computation time. For result and discussion, let's start with substrate deformation. On the screen right now shows the data of distortion for its source model for double ellipsoid at the end of the increment of 3680. The figure is the visualization of the substrate deformed along the displacement in y direction. The distribution of the displacement on the substrate can be examined through the contour shape and colors. It shows that the highest distortion of the substrate were on the right and front side, with the value of distortion at the last increment is 2.06783 mm. Here is the visualization of distortion of substrate of the rectangular source model. The highest distortion of the rectangular source model were on the right and front side, with the distortion is 2.06975 mm. The graph illustrates that the distortion shape from both one model is almost similar. However, from the tabulated data, it shows that the rectangular source model produces more distortion at the right and front side of the substrate, while double ellipsoid byproduct produces more distortion at the left and rear side of the edge. Next, we proceed with the thermal distribution result. On the screen right now is the visualization of temperature distribution of both one model after the final increment. Temperature distribution for both double ellipsoid and rectangular source was similar at the end of the simulation. To access for every data of temperature distribution history at every increment of both one model, all the result of temperature were taken at heat affected zone location node of 19539 for both one model. All the data were plotted on the next graph. Figure 15 and 16 shows that the distribution of temperature along the increment at node 19539 for both one model was similar. Based from the graph, the starting of simulation was set at ambient temperature of 30 degrees. The temperature then was rapidly increasing during the movement of wet filler at the first string of first layer due to high power input, until it reached 463 degrees at 1 to 6 seconds of simulation time. It's shown that the temperature was reached at a peak during the cooldown of third layer of the model, which is at increment of 937 at simulation time of 595 seconds. Here is the table shows the temperature distribution at every end of layer and cooldown phase. The value of the temperature were taken from the history path of the numerical simulation. At the end of the numerical simulation, the computational time for both models is also compared. Computational time is an overall time consumed to complete the numerical simulation for both models. Table 7 presents the comparison of total computational time between these two models. The rectangular source model consumed least time to complete the numerical simulation. The data were taken from the wall time in the log file of the simulation, where the log file is the file that records either events that occur in the operating system or software runs. That's all the result for this project. For significance of work for this study, working more efficiently and effectively is made possible by utilizing software, a factor resulting in part from the high cost of material and the restricted amount of the time available for the work in the welding workshop. From the computational time analysis, the rectangular source model has the low computational time, which can be explained by the fact that its rectangular shape is simpler than the weld with modeling geometry that has been to be calculated. This technique will be enhanced and shorten the time in order to calculate the expected duration or other required result for the future study. In conclusion, it is possible to conclude that the modeling and simulation have been effectively completed using FEM method. The numerical simulation was carried out with two different heat source models, which are double ellipsoid by Goddard and rectangular, and the following information can be presented as the outcome of this conclusion. First one is 10 layers and 3 strings of one model were included in the numerical research, which was successfully complete, and the simulation method is both well structured and straightforward. Next, at the end of the FE result, it seems that the deformation produced by both simulations are virtually identical in terms of distortion and similar in this temperature distribution. It is essential to note that the heat source model has a significant impact on the temperature distribution of heat effective zone, and the optimal model should be selected based on which welding technique is being employed. At the end of the conclusion, although increasing the amount of increment and utilizing a final mesh will significantly enhance simulation accuracy, and the computation time is a limiting element that must be taken into consideration in any simulation of this kind. So here is the end. Thank you for spending your time for watching this video. I would like to take this opportunity to thank you to all the lecturers, staff and my fellow friends for the knowledge and support over the years during the time in UATM Shah. For any question regarding to this video presentation, you can reach me with the detail that I provide on the screen right now. That's all from me.